Hey everyone, welcome back, and we're moving on to question 23 in the 2019 B test. This is actually one of my favorite problems, and it's also really fun. The question reads, a train travels at 360 kilometers per hour on an almost straight track. The track is slightly sinusoidal, with a vertical amplitude of h over a 1 kilometer distance as shown in the figure. If the maximum tolerable vertical acceleration of the train is set at 0.1 meters per second squared, what is the maximum allowable size of h? So I actually bet that everyone's first instinct when solving this problem, this was also my first instinct, is to look at, well, if we know that the acceleration max is equal to 0.1 meters per second squared, and we also know that the acceleration due to centripetal acceleration is v squared over r, then why don't we know what v is, 360, so we plug it in and we could find r, and then we use r to find h, right? Well, here's the problem. Well, we find r is like what, 300 meters, whatever, it doesn't matter. Okay, and then it doesn't really mean anything to us, right? We have a radius r of 300 meters that it would allow for the a max to be in this range, right? But that doesn't tell us anything about the height because it's just sinusoidal. It doesn't have anything to do with the circle right here. But if you know how to do it this way using the radius method, then please message me because that'll be really interesting. But anyways, I guess my thought process after seeing that this didn't really work is to really think about like what else can we do to look at the acceleration of to model the acceleration of the block. And actually, if you can think about basically like if you're looking at the block, say you're like a really large observer and you're looking at it head on, you're kind of just seeing the block oscillate up and down, right? Up and down. And it's kind of like moving like a spring. So that tells us, why don't we try to model it like a spring and see, because we know how to find the acceleration of a spring, right? So let's first try to model its uh, movement up and down. So I'll call that y. So y is like, say y0 is right here, and then y is equal to h when it's at this part right here, right? So y is equal to the amplitude, which is h, and then I'm just to say sine, right? Because it's a sine curve starting at time is equal to 0, and then times omega t, okay? So actually, let's think about exactly what omega is in this equation. Omega t, so basically this omega will tell us how fast it's the angular frequency, so how much time does it take for it to undergo, sorry, how many radians is one revolution? Wait, hold on. Yeah, sorry, this omega right here is kind of hard. It's a bit weird because you can't get it confused with omega for angular velocity, but omega is actually the angular frequency, which just means frequency times 2 pi. Basically, let's try to figure out what's the frequency of the angular frequency of this wave. We know that angular frequency is equal to 2 pi times the frequency again, and frequency is equal to 1 over period, right? So angular frequency is 2 pi over period, and we actually can calculate the period because we are given the initial velocity of the block. So and we know, as we all know, velocity times time is equal to distance, right? And we know the velocity is 360 meters per second, and it's going to be constant. I think the equation says it's constant throughout the motion. And then times the period is equal to the distance of one revolution. So you might be freaking out like, oh my gosh, I need to do a line integral and figure out the exact distance of this sine curve, right? But if you look at all the answer choices, they're all on the range of like the maximum is just 10 meters of height. And if you think about it over 1 kilometer distance, 10 meters of height is really not going to make a difference. So we can just approximate the distance to be 1,000 meters. So we get that the period is equal to 1,000 divided by 360, about 2.78. So, and then if we just do 2 pi divided by period, then we get that the angular frequency is 2 pi divided by this number is about 2.26. Okay, so now we can plug this into this equation. So the y is given by h times sine of 2.26 times time. And actually this will give us the answer, because what we can do is we can take the double derivative of y, right? And that'll give us the acceleration in the y direction, which is what we want, right? The maximum tolerable, we're looking for the vertical acceleration of the train, so we take the double derivative of y, we get the vertical acceleration of the train. And then if you calculate the double derivative, you're basically just taking this guy out twice, the coefficient in front of here twice, so you get 2.26 squared h times sine of blah blah. But anyways, this is the acceleration, but all we care about is the magnitude of the acceleration, right? Because we're just looking at the maximum a. So we know that a max has to be less than 0.1. So let's look at what happens when this equals this a, which is going to be 2.26 squared times this height, right? And then we isolate for the height. So that gives 0.1 divided by 2.26 squared, about 0.195. So it's about 0.2. So that gives us I made a little. I made a little bit of rounding error because this thing is not actually very rounded. But I think if you plug in all the numbers exactly how they are, 1.1 divided by Sorry, so I actually made a little mistake with units here. This is 360 kilometers per hour, and this is 100 meters, so it doesn't really make sense for me to say it this way, so I should have done I should have just kept this in kilometers, 1 kilometer. Okay, and then now we could change this to minutes, to seconds, so that's just 360 divided by 3600, right? Because there's 3600 seconds in an hour. And that gives us 0.1, right? And times t is equal to 1. So t is not actually this, t is actually 10 seconds, okay? So when we calculated this, we also calculated it wrong. It's going to be 2 pi divided by 10. That gives us 0.63 about. Okay, and then when we plug in here, this all the other reasoning is fine. It's just that the number is a bit off. This is 0.63 about, so this thing squared. So then if we plug it in to here, this thing is 0.63 squared. We get that h is actually 0.25 meters, right? So that gives us 25 centimeters as the answer. If you don't know calculus, you actually didn't need to do this part of taking derivatives, because if you remember, the acceleration of a spring or the acceleration of something oscillating is just omega squared times the amplitude, right? If you didn't remember that, then you could have solved it using calculus.